Hello, class. This chapter will cover electric potential. First, let's start with the definition of electric potential energy. A great analogy is gravitational potential energy. You can think of electric field lines as gravitational field lines which points towards the center of the Earth, and the positive charge particle as a rock. If you hold a rock up in the air, it has high gravitational potential energy relative to the ground. If you drop the rock, it will lose potential energy but gain kinetic energy. This works the same way for a charged particle. If you place a positive charged particle at a high electric potential energy point in the electric field, it will move along the electric field lines and gain kinetic energy while losing potential energy. It's not shown clearly here as it does in the emailed notes, but the change of potential energy equals negative work, where work done by the electric forces equals negative QED. Recall, letter A and B represents initial and final respectively. Oh, the reason why the electric field strength across the plate is the same is because the field lines are equally spaced, meaning the electric field strength is the same in that area, whereas a charged particle, the electric field lines either radiate inward or outward, depending on whether it's negative or positive, which causes the electric field lines to spread further and further apart as you move away from the charged particle. Thus, the electric field strength will vary. We'll discuss this in class. The definition of electric potential is electric potential energy per unit charge. The unit is V for volts. The electric potential difference, or also known as voltage, is the change of electric potential between 2 points. In this slide, they use point A and B as their 2 points for initial and final. Recall that the change of potential energy equals negative work. The more massive the charged particle, the larger the potential energy. Just like with gravitational potential energy, the more massive the rock, the larger the potential energy will be. Here's the rearranged voltage equation to have work equal negative Q times voltage. Also, recall that work equals QED. If we combine the two equations, we get an equation for electric field, which equals a negative voltage divided by the distance between point A and point B. Here's an example. Press pause to solve. Suppose an electron is accelerated from rest through a potential difference of positive 5,000 volts. What is the change in the electric potential energy of the electron? Using this equation below, you plug and chug and you get negative 8 times 10 to the negative 16 joules. What is the kinetic energy? Recall, change of kinetic energy equals negative change of potential energy, so the answer is a positive value. Now, what is the final speed of the electron? Using the definition of kinetic energy 1/2 mv squared, we can solve for the final speed. Next example. 2 parallel plates are charged to produce a potential difference of 50 volts. If the separation between the plates is 0.05 meters, calculate the magnitude of the electric field in the space between the plates. Using this equation for voltage, we solve for E, you get 1,000 volts per meter. Note, I didn't put the negative sign because they just want the magnitude. Equal potential lines indicate where the potential is constant, as seen as a green dashed in the figure. Note that they are always perpendicular to the electric field lines. Here's an example of equal potential lines for 2-point charges. Again, anywhere along the green dashed lines, the potential is constant at a particular value. So each green dashed line would have a different constant potential value. This figure shows those potential difference values at each equal potential line. So 10 volts would be anywhere along that particular green dashed line. Last definition. Electron volt. 1 electron volt is the energy gained by an electron moving through a potential difference of 1 volt, which refers to this equation below. 1 electron times 1 volt equals 1 electron volt, which also equals 1.6 times 10 to the negative 19 joules. Use an electron volt as units for energy instead of joules is easier when dealing with charges. The end.